So I'm going to start with a nature myth right now. That's our first nature myth this evening. And that is poisonous daddy longlegs. Maybe you have heard it said that daddy longlegs are the world's most poisonous spider, but their fangs are too short to bite us. Now, I know that when I take a group of kids out and we find a daddy longlegs, and these are very common organisms, that every time I pull up a daddy longlegs and ask the kids about the daddy longlegs, somebody says, daddy longlegs are the world's most poisonous spider, but their fangs are too short to bite us. Okay. Well, it turns out that is not true. That is our first nature myth for this evening. And here's why it is not accurate. I'm going to take this myth apart and show you why it's not accurate. Our daddy longlegs, these they're called harvestmen. They're in the order Opiliones. They're actually not spiders. They are arachnids. They are related to spiders, but they are not actually spiders. And not being spiders, they do not have any fangs. So they have no way of piercing your skin in order to administer any venom. And as far as we can tell, there are no venom glands even in there. If you take a look at this picture right here, you will see and compare the jaws of a jumping spider, which is a true spider and does poison its prey, with the harvestman's jaws. So a spider has fangs with which to inject the poison. Harvestmen have little pinchers, like little crab claws right there. And they use those little crab claws to tear apart their food and eat it in pieces. A spider injects the venom. It's got two purposes: one, to stun the creature that they're eating, and the other purpose is to liquefy their insides, and then they suck out the insides of the organisms that they've captured. All right. Well, harvestmen don't do that. They eat their food just like you and me, in pieces with their hands, not really their hands, but their mouth parts, but they tear up their food and eat it that way. So they don't have any use for poisoning anything because they don't feed that way. Now, how do we get here, though? How do we get to this idea that daddy longlegs are not just a spider that's poisonous? They're not spiders at all, but they are the most poisonous spider. Okay, where would that come from? Well, let's look at another daddy longlegs. Now, around here, I've grown up just over the border in Ohio and here in Pennsylvania. Every time somebody talks about a daddy longlegs, they are talking about the harvestman spider, that thing with those single body part and the long legs that is just real common and just walks all around with it, doesn't have a web or anything like that. But some people may think of daddy longlegs, they may actually think of a type of spider. And in other countries, for example, this seems to be maybe a little more common. I don't know. Again, I'm speaking more from the Northeast. I haven't heard this spider called daddy longlegs. But if you think of the spider that you see in the basement or in the garage with the long legs, and it makes all the cobwebs and things like that, it has a real skinny body and long legs. Well, some people call that a daddy longlegs. And it does have venom and fangs because it is a spider. Okay. However, we do have some evidence that it is not a particularly poisonous, strong. It just has venom, but it is not a particularly strong venom. And what is our test for this? Well, we are going to go check in with Adam Savage from Mythbusters. And if you know Mythbusters, it was a very popular program on cable where they would test myths. And they tested all sorts of things. They tested movie myths, they tested folklore, they tested medical myths, all sorts of things. All right. And what they would do is they would try to be as scientific as they could. Now, they had some fun with it, and they recognized that, but they would be as scientific as they could. So they explored this idea of a daddy longlegs, and they said, well, maybe it is this daddy longlegs. Let's see how poisonous it is. Okay. And so what Adam Savage did was he volunteered to be bit by the venom of a daddy long-legged spider, one of these regular spiders of daddy long-legs. And he did not have any particular effects from it. So that was his. I wouldn't recommend that way of testing things, but that just goes to show you what you do. Okay, how do you prove this myth, or how do you prove that it's true or that's false? Well, you test it, you try it out. Okay, so all of our myths tonight have a little lesson that we end with. So our lesson right now to begin us with, to get us going into these nature myths, is to don't repeat a cool fact without checking it. All right. The daddy longlegs being the world's most poisonous spider, but he has fangs too short to bite us. Sounds great. It is a wonderful thing to tell to a group and to get to admire the daddy longlegs, but unfortunately, it is not true. So when I hear a really cool fact, I need to think about it with some skepticism and evaluate it to see if it's something that I want to continue including in my programs, or telling my friends and family, or even just incorporating into my own personal knowledge base. So don't repeat a cool fact without checking it is our first lesson. Now I have a test for you. For our next myths, that's kind of our opening myth, kind of gets us in the mood of what we're going to do. We have a myth. We're going to see what the research is or what the evidence is behind it, and then decide if there's any truth or fiction to it. I have these are the myths we're going to take now. We're going to test. I have a test for you. All right. I want you to look at each of these myths. There are 10 of them, and you decide if you think they are true. Now, I say the word myth, but I'm using that in a loose term. Just these are nature facts. Okay. Some of them are myths. Some of them are true. I'll tell you right now, but I'm not going to tell you which ones until we get to each as we go. So let's do a little test here. We're going to go through 10 of these. I want you to think about whether you think that this particular, maybe you've never heard of it. Have you heard of it? And if you've heard of it, do you think that it's actually true? Okay. Myth number, or conjecture number 1, raccoons wash their food. Okay. Raccoons wash their food. Item number 2, wood frogs can survive freezing solid. Do you think that's true, false, or somewhere in between? Item number 3, goldenrod can aggravate your allergies. Goldenrod can aggravate your allergies. Possums can hang by their tails. That's another one we're going to look at tonight. Do you think that is true or false? Possums, we have 2 possums tonight. Possums can eat 5,500 ticks in a season. Have you heard that one? That's a relatively new one. We'll talk about that one. Plants breathe carbon dioxide. Is that accurate? Do plants breathe carbon dioxide? Ben Franklin proposed the turkey as the U.S. symbol. Have you heard that one? And how true is it? Peregrine falcons can reach 200 miles per hour. Have you heard that one? And is it true? No 2 snowflakes are alike. Another fact, or is it? And finally, woolly bears can forecast the weather. Woolly bear caterpillars can forecast the weather. All right, so that's where we're headed tonight. We're going to deconstruct each of these and see where the truth lies. Raccoons habitually wash their food. Is that true or is it false? Okay. It is true that raccoons have been observed washing their food. That is true. That has been documented. However, here is the shocking truth. That washing behavior has only been observed in raccoons that have been in captivity, that are in a cage or an enclosure. It has never been documented in the wild. So raccoons do not find a bird egg way up in the top of a tree, carry it down, and wash it. Okay. The only time they wash their food that's been observed and do it consistently is if they're in captivity with water nearby. Okay, like a water bowl or maybe flowing water in a more elaborate enclosure. Okay, so and they'll douse their food in that. Nobody really knows why, and part of the reason nobody really understands why is because nobody's seen them do it in an actual cave, in an actual out in the habitat, out in the wild. And I think what's happening is being in a cage is triggering some sort of instinct, if you will, that just being in an enclosure and being like captive next to water, they go wash it in the water, but they do not seek out water to wash their food in the wild. It has not been observed. So raccoons wash. So our lesson here is that captivity can change behaviors. If you're watching something, keeping it in a box and seeing what behavior it has, that may not apply when it is actually out in the wild. And that's important. So if you're evaluating things, maybe even evaluating a scientific paper, okay, that has been looking at some phenomenon. Is there something about the way they're doing it? Is it how close is it to nature? And then you know for sure whether it is true. Now, this raccoon thing has been going on for a long time. In fact, in German, they call the raccoon a wash bar because it washes its food, but only in a cage. Next up, wood frogs. I'm sorry, the lesson here is that captivity can change behaviors. Sorry, I'm working with my screen here, and I'm one screen ahead of you guys on my little helper, and so I'm not hitting my key in just the right moment. I'll get my rhythm down here. Okay. Next up, wood frogs can survive freezing solid. I don't know if you've heard that. I've heard all of these at one time or another. And is it true or not? Well, it turns out that yes, it is true. Wood frogs and a couple of other amphibian frog species can actually survive freezing solid, just like our picture shows. Some frog, in a chunk of ice, thaw him out, he survives. Kind of a miraculous property of these frogs. In fact, they've studied this property to see if there's something they can use for, say, hypothermia victims or frostbite or something like that. Okay. And they've studied this now, and they've isolated some of the compounds that are able to do that. Well, how do we know that it is true? Well, it turns out a 1992 studied collected frogs from the wild and froze them. There you go. So how can you tell if something can survive being frozen? You freeze it and see what happens. And in this 1992 study, they did. Now, the thing is, this idea of frogs surviving being frozen has been studied before 1992 on a couple of occasions. There were two other studies that studied this. But the two previous studies, I think one in 69, one in 83 or something like that, concluded that the frogs could not survive freezing. Okay. What was the difference? Well, those early experiments that concluded that they could not survive, but the experiment procedures were not really mimicking natural conditions. They were really being a little too rough on the frogs. They were freezing them too abruptly. They were not mimicking a more gradual cooling down that they might have as the fall wears on, or as it begins to frost and gets colder and colder. The frogs and they're buried in leaf litter. All those conditions and the timing and the gradual process of moving down into that state, they can withstand that. Pop them in a deep freeze? No, that's too much. But give them natural conditions, and yes, they can survive freezing in the wild. So our lesson here is that one experiment is not the last word. If you'd seen that experiment in 1969 or 1983, you might think the question was settled. Oh, that's just folklore that a frog can survive freezing. But it's actually true if you did the experiment right and got it to mimic native natural conditions you could prove and demonstrate that indeed they can thaw out from freezing solid and survive. Our next myth up tonight: goldenrod pollen aggravates allergies. Now, this is a bit of a tricky one here because a lot of people already blame ragweed. They know enough about goldenrod that they know that it's not the thing that causes allergies, and so they blame ragweed, which grows at about the same time in some of the same places. Okay, so let's take a closer look at that. Let's compare goldenrod and ragweed. Now, here's the difference between them. Goldenrod is pollinated by insects. Ragweed is pollinated through the air. So if you want insect-friendly pollen, to move pollen from one plant to another to fertilize the flower, you are going to need to have sticky pollen. This is going to stick to the animals. If it's going to stick to the bees, it's going to have a hard time getting up into the air because it's sticky. It wants to stick to the things that come to the plant. It's not trying to get them through the air. If you are an air pollinated or wind pollinated plant like ragweed, then you want to have your pollen get cranked out into the air, get airborne, catch the breeze, and fly off and run into some other plant. Okay, so that's how the story goes. Goldenrod does not cause allergies because the pollen is not airborne. Ragweed is the one that causes allergies because the pollen is airborne. Okay. However, I don't know if you noticed that in the corner, but a little asterisk just showed up. When it comes to myths and truths and nature facts, the asterisk is a bit of a nuisance. Whenever you see that asterisk, this means there's more to the story. Here's the asterisk to the goldenrod versus ragweed pollen. It is true that ragweed is the thing that causes your allergies, okay? But when florists work closely with goldenrod, they can have an allergic reaction to it, okay? Why is that? Because goldenrod and ragweed are related and they are both allergenic. The pollen in both is allergenic. The difference is it's much harder to get a nose full of goldenrod pollen because it's sticky. It's meant to stick to insects. The ragweed gets into the air. So sometimes people who do walk through a field of blooming goldenrod, like right now here at Beechwood, we have a nice field of blooming goldenrod. And on a nice day, maybe there's a bit of air moving around, some of that pollen can get up into the air and you can have an allergic reaction walking through a field of goldenrod because you're reacting to the goldenrod pollen. But you don't see the goldenrod count on your allergy app because it is not the one that is airborne and all over the place. A ragweed pollen is everywhere and you'll breathe that no matter where you are. Goldenrod, you'll just run into that if you happen to get your nose way down into a goldenrod plant or into a field of goldenrod. So our lesson here is that nature is not good at absolutes. Okay, whenever you say something is always this or something is never that, nature has a way of not agreeing with you. There's an exception to every rule, and nature is no exception to that rule. So, and anytime you hear a nature fact that says, "Oh, it's the most poisonous spider," or that thing does not cause any allergies at all, those kinds of absolutes, those kinds of blanket, large, big statements often have asterisks attached. There's often exceptions to that. All right, let's talk about possums. Opossums can hang by their tails. Is that true or false? Is that true or false? Well, yes, it is true that possums can hang by their tails, and we have photographs. There's one right there. a genuine opossum, Virginia possum, not some exotic possum from Australia, Virginia opossum hanging by his tail. But there's an asterisk. Here's our asterisk. But only briefly when they are young. Their tail is grippy, it's prehensile, but it's not like a monkey's tail that's strong. Okay. It's like a little extra prop for them. The babies can hang, but briefly. The tail is not strong enough to support them. Okay. So while it is true that they can hang by their tail and that who do have a prehensile tail that can grip and curl around things and hold on, it is not strong enough for an opossum beyond its youngest days, except when it's a baby. And even then, they don't hang from a branch the way that they sometimes see in a cartoon or something like that. It's mainly just to hang on to something briefly while they are moving one spot to the next. So we have photographs, but our lesson here is sometimes pictures don't tell the whole story. It's easy to get a picture of something suspended in time and it looks like it's doing this thing all the time, when really it's just that you've just captured it at that particular moment in some unusual or pose. And so you need to keep looking to see if true, if it happens all the time, or maybe just you happen to catch it at some weird moment that made it look that way. So pictures don't always tell the story. All right, here is a more fresh nature fact or myth. And this one was one that made the rounds here at Audubon among our naturalists, because this study came out in 2009. There was a 4-day study of captive possums, and they extrapolated. They put ticks on these possums, and then we came back later to see how many ticks were still there. And they figured that any tick that was missing must have been eaten. Okay. And over this 4-day period, and they extrapolated that, the number of ticks that looked like they got eaten. And they extrapolated that to an entire season. So whatever they ate in 4 days, whatever dozen or something ate in 4 days, or 100 ate in 4 days. Well, then they said, well, over a season of, whatever, 6-8 months, it must be 5,500. Okay. All right. So there's a couple things wrong with this. And the most important clue that there's something wrong with this experiment is this. Somebody went out into the wild, picked up possums that had been roadkilled, examined the contents of their stomach, and they found no ticks in the stomachs of these possums. Okay. Which is disappointing, because we are excited about this fact about possums, because it means for another reason to love opossums. I mean, everybody loves an opossum, but another reason to love opossums. And the fact that maybe they can help us with our tick battle with so many ticks. Well, it turns out they don't really. If they do eat a tick, it's just incidental. Okay. And it also stands to reason that they're going to go around and find ticks and consume them deliberately. You know how ticks are. They're pretty sneaky. They're hard to find. So it doesn't quite match up with experience or logic. The trouble with this is that it was just a 4-day study, and their method was they just assumed that if they couldn't find the tick, that it must have been eaten after they inoculated the possums with these ticks. And so they didn't examine the contents of the possum stomach to see if that's where the ticks went. So it was a poor design. It was ambitious math, and it did not hold up to actual scientific observation when we went to look at these possums in the wild. So our lesson here is read the fine print. Maybe you find a study that backs up your nature fact, but take a look at the study. Is the study well designed? Does the study answer the question that you have? And does the study demonstrate significant evidence that your fact is true, or that your fact is disproved? Okay. Does it study? Read the fine print, check it out, see if it tests what it should test. Is it mimicking real world conditions? or just making assumptions that my animal in a cage is going to tell me is exactly how they would behave out in the wild. All right, so our lesson here is to read the fine print. Here's one. Plants breathe carbon dioxide. Plants breathe carbon dioxide. So this is a kind of a handy shorthand, right? Like humans, animals breathe oxygen, but plants breathe carbon dioxide. Okay. And it can be kind of a handy shorthand to sort of explain the difference between plants and animals. And in a way, there is a truth to it, in that plants do definitely use carbon dioxide. Okay. But to say they breathe carbon dioxide in the same way that we breathe oxygen, well, guess what? That's not really quite accurate. Let's take a closer look at how that carbon dioxide is used. This is photosynthesis. Photosynthesis, that's how they're using the carbon dioxide. They're using it for photosynthesis. And photosynthesis is what they're using to make their energy in order to do their body processes. We cannot do that. We must rely on plants to capture the sunlight and turn it into a usable energy. Okay? Plants, that's how they use the carbon dioxide. They're going to use it for photosynthesis. They're going to take the carbon dioxide, a little bit of water, going to add some sunlight, use the sunlight with these compounds inside the chloroplast and all the other stuff that goes on in there. We're keeping it simple tonight. And what are they going to get on the other side of this equation after they're photosynthesizing? They're going to get some oxygen, which they release as a byproduct, and they're going to get energy, but not energy directly. They are going to lock the energy into molecular bonds, and they're going to be the bonds in sugar, in forms of sugar. Okay. That is the end point of photosynthesis. It is not they take the energy and just power their bodies directly from photosynthesis. They make sugar. Okay. The energy is locked in the sugar. We have to get it out. How do we get it out? How do we get it out? Well, we eat the sugar and then our body burns the sugar. The plants are doing the same thing. That energy is locked up in the molecule, in the bonds of the sugar molecule. We have to respirate to get the energy back out. Plants must respirate to get the energy back out. What's respiration? It's that bottom equation. You take the sugar, you add oxygen to it. The oxygen helps break apart the sugar molecule, and out the other side, you get the energy that you can power your cells with, and you get carbon dioxide and a little bit of water as out the other side as well. Okay. So the upside of the point of this is that, I'm sorry, I am one thing ahead here. Here we go. Here's our thing. We've got sugar and we add oxygen to it, and out the other side, we get energy and we get carbon dioxide. Okay, so you see that? It's kind of the reverse. Photosynthesis puts it into sugar. Respiration takes the energy back out again. But this time when we take it back out, we're able to get it in a usable form that our cells can use. That our mitochondria, the powerhouse of the cell, is able to use the energy that it's in the form when it comes out of the respiration. Okay. All right. So respiration extracts the energy from the sugar. And the bottom line here is this. Plants must breathe oxygen to use the energy that they stored during photosynthesis. So plants do not breathe carbon dioxide at all. They certainly absorb carbon dioxide. They use carbon dioxide to make sugar, but then they have to breathe just like the rest of us. Not with lungs, but still with exchange of air, with oxygen to break down the sugar to get the energy back out. All right, now this might seem like a bit of a finer point to you, but we're headed somewhere. Take a look at this. We just said that the plant has to break down the sugar molecules that it made in order to get the energy back out in a usable form. It cannot use the energy from the sun directly. Okay. This is the carbon budget of a tree. That carbon dioxide that comes into the tree or into the plant, what happens to it? Well, It's going to all get photosynthesized. All the carbon dioxide is going to get photosynthesized into sugars. Okay. About half of that sugar that's photosynthesized is going to be respired. It's going to be burned up with oxygen and turned into energy and then waste as carbon dioxide as a waste, okay, as a byproduct. But not all of it. Half of it is going to become structure for the plant. It's going to use those same sugar molecules, stack them together to make starches and lignins and cellulose and all sorts of other useful things, okay? And that's going to become the tissues, the structure of the plant. That's where half of that carbon went to from the photosynthesis, all right? Half to the energy, half to the structure, but it's not going to stay in that structure forever. That plant is going to eventually die or drop its leaves, and it's going to decompose. And all the energy, all the carbon that went into those tissues is now going to be used by bacteria and by fungus, okay? And it is going to be broken apart. That energy that was locked in there when the photosynthesis happened, they're going to break that apart. They're going to take the energy. They're going to use it now, and they're going to produce good old carbon dioxide as a byproduct. So all the carbon that goes into a plant as carbon dioxide is going to come out again, okay? So this is where we get to where the myth can lead to some extra bonus myths tonight. All right. So if we don't understand exactly how plants use carbon dioxide, we just say, okay, plants breathe carbon dioxide. Yay for the plants. They can use carbon dioxide. That's great. Okay. And we've been talking a lot in recent years about excess carbon dioxide that is getting into the atmosphere from our burning of fossil fuels. Okay. What about that extra carbon dioxide? Well, if you don't understand how this whole photosynthesis thing works, you can come up with draw some wrong conclusions. So 2 bonus myths. Bonus myth number 1, extra carbon dioxide is okay because it is a plant fertilizer. I've heard that. Carbon dioxide, it's going to make the planet greener. The plants are going to use that carbon dioxide. Okay. Bonus myth number 2, extra carbon dioxide can be removed by planting trees. Well, everybody loves a tree, right? So if we plant trees, we can soak up that extra carbon dioxide and we'll be happier. So yeah, greener world. Okay, so yeah, carbon dioxide, it kind of sounds like carbon dioxide, extra carbon dioxide might be a good thing. But remember what we just said about how a tree uses carbon dioxide, how a plant uses carbon dioxide. It's a yes, but. Yes, carbon dioxide encourages plant growth. Yes, carbon dioxide can be removed by planting things. But half that carbon dioxide, half of that carbon, or carbon dioxide is the form it's going to come out as, is going to be put back into the atmosphere right away because the plant has to metabolize it to get the energy back out. Has to metabolize that carbon compound, the sugar compound, to get the energy back out. The other half of the carbon that's going to go into that plant is going to come out again eventually because when the plant decomposes. Okay. All right. Now, I have a disclaimer. Planting trees is always a good thing. Don't get me wrong. Planting trees is always a good thing. Okay. But we have to understand that oversimplification can lead to misunderstanding. Okay. You may think we can solve this problem or something could be a good thing because, oh, carbon dioxide is a good thing. There's a lot of it. More of it must be better. That's not always true about something like this. We oversimplify our understanding of how plants and they use carbon dioxide, and it can lead to wrong conclusions about, in this case, effectively solving a problem. Okay. All right. That's your sermon for tonight. Let's move on. How about Ben Franklin and the turkey? Ben Franklin. This is the is it a fact? Is it a myth? Ben Franklin proposed the turkey as the United States national symbol. Okay. I've heard this one. But if you take a closer look, there's more to the story. By the way, I'd like to thank AI for providing this helpful picture of Ben Franklin with his favorite turkey. And I was thinking it was a pretty good picture until I was looking at it tonight, and I realized, in fact, I thought, well, he's doing pretty good. He has the proper number of fingers. That was pretty good. The turkey has the proper number of wings and so on. But then I realized that Ben Franklin's eyeballs and the turkey's eyeballs are the same. They gave Ben Franklin turkey eyeballs. So, oh well, never trust AI. Here's the real story. Here's the real story of this. It is true that Ben Franklin did propose or suggest that the turkey might be a good symbol of the United States. He did actually say things along those lines. However, he never said those in any kind of committee that we know of. He was on an early committee deciding on symbols for the new nation. No record ever shows him proposing the turkey at that time. The document that we have where he does talk about turkeys was never published during his lifetime. It was only published later after his death among his papers and by later biographers. They found this document and they said, oh, this is fun, and they published it, okay, where he talks about turkeys and how they might be a good national symbol. However, it was where he did it was actually a form of political satire. He supposedly wrote a letter to his daughter where he talked about suggesting that turkey would be a good symbol. The thing was, Franklin, as a rule, did not write about politics to his daughter in the real letters to his daughter. He wrote this as kind of a pretending to write to his daughter, as kind of an offhand way of, saying something without actually saying it. You know what I mean? Kind of being cagey about it, kind of being ironic about it. That was what he was doing. It was political satire, kind of like Jonathan Swift and his proposal to eat the babies. Okay, that famous one, his modest proposal from Jonathan Swift. It was satire. It was not something that was necessarily done. It was meant to make a point, but it wasn't necessarily a literal situation where he was deliberately proposing this. Okay. So what was he doing when he was talking about this turkey thing? Well, it's actually part of a much longer letter. And in this letter, he was spending a lot of time scolding the Society of Cincinnati. The Society of Cincinnati had kind of this thing like, hey, wow, we got this new country. It'd be cool if that we had some hereditary titles and stuff, like we used to have back in England. Okay. Or, remember, the America's mostly the rabble, so they didn't have titles to begin with. They're like, well, we got a new nation. Hey, we should make ourselves some titles. And while Franklin greeted this with a jaundiced eye, and he said, I noticed something just recently. I've noticed the Society of Cincinnati has adopted the eagle as its symbol. That's kind of nice. But then I've been looking at some of the artwork, and I'm looking at this eagle, and I'm going, you know what? That looks a little like a turkey more than an eagle. And if you look at these illustrations I have over here, there's some of their letterhead, and here's a medallion that they made. And you can see their concept of an eagle seems a little stretched out. Okay, it's got kind of the proportions are not quite there. It looks a little bit like a turkey, don't you think? And he goes, their symbol's supposed to be an eagle, but it looks a little bit like a turkey to me. And you know what? Come to think of it, the turkey might be a better symbol after all. The eagle, he steals his food from the osprey. He's a bit of a thief. But the turkey, he defends his flock. Early America, we were defending our flock. We were not stealing from others. Britain was the one stealing from us, right? And, we were defending our flock or whatever. So he kind of goes on this little tangent about eagles versus turkeys. Okay. And that's as far as it went. All right. So he did this. And as I say here, it was inspired by bad art. He looked at these things and he was riffing on this rather tacky art that he saw with them. He said, "Yeah, you know what? I think we should go with the turkey because this eagle thing." And he was kind of mocking the Society of Cincinnati and some of their ideas about aristocracy and inherited titles and things like that. So the lesson here is that context is important. Did 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 the words that the turkey might be a pretty good symbol for the United States, maybe even better than the eagle? Did he say that? He did, but it was in the context of satire. He was using it to make a point, okay, about a political situation. Another little piece of this puzzle is that why didn't you say it out loud about complaining about the Cincinnatians? Why did you use satire? That was because he was our ambassador to Paris at the time, and so he had to be very mum about his personal political views, and this was kind of his way of saying that. But because he was an ambassador, he wrote this little faux letter, this little satire, but he kept it in his papers. He showed it to a few people, and they're like, "I don't think you should really publish that." So he's tucked it in his papers, and it was found in his papers after he died. It was never meant for public consumption, or never finished in that way. All right, peregrine falcons can reach 200 miles per hour. Now, this figure, 200 miles per hour. This has been around a long time. This figure, where do we get it? Where did it come from? It came from the original number is from a figure, and what a quote from an airplane pilot who was flying, and he noticed a peregrine falcon pacing him or keeping up with him. Okay, this is back in 1930. And he knew his airspeed, which was apparently over 200 miles per hour at the time. And so he reported that this peregrine falcon was traveling as fast as he was, 200 miles per hour. And that became the fact. Okay, that became the fact. But it was very difficult to test. It's all anecdotal at this point. We have this pilot who said it. There's been a couple other pilots who've reported similar things. There have been some skydivers who noticed falcons pacing them or following along or whatever. Okay, so there's been some observations of that. So lots of anecdotes. There's been some aerodynamic theory, putting the shape of a falcon in a wind tunnel and seeing what it could handle. And well over 200 miles an hour in a wind tunnel, something like 300 miles per hour. Okay, just as far as his aerodynamics go. He's built like a stealth fighter, and the shape of a stealth fighter is a lot like the shape of a peregrine falcon. So there's aerodynamics are in the peregrine falcon's favor. And then there's a National Geographic episode that was about, I forget, about 15, 20 years ago already. No, 1999. 1999, a falconer for National Geographic episode tested this. And what he did was he took his falconer up into the plane with him. He was a falconer and a skydiver. Important piece of information. He was a falconer and a skydiver. He took the falcon up with him in the plane. He tossed the falcon out of the plane, and then he jumped out. And then he would put his hand up and call the falcon in. And the falcon could, no matter how fast he was falling, the falcon could catch up to him. Okay. And they documented this. They showed it on camera, and they put like a sensor on the falcon to see how fast he was going. They could test his airspeed when he was doing all of this. Okay. And they clocked it from the ground and so on. All right. And they got him over 200 miles per hour when they did that. Okay. The thing is, so there you go. They did document that. with technology and everything else. However, so yes, they can reach 200 miles per hour. The wind tunnel says it. Several observations suggest it. Okay. But then the next question is, but do they in normal conditions? Or are we talking about something that's extraordinary? Think about this. The guy in the National Geographic special, he took his Falcon with him and he tossed it out of a plane that was already moving at X hundred, whatever, 100 some miles per hour. Okay. And clearly the Falcon is capable of some serious movement, but he got a boost. Okay. He got a boost by being thrown out of the plane. So we're not talking about just flying around and deciding he's going to go catch something. Okay. Can he crank it up to 200 miles per hour just from a perched on a cliff or just hovering in the sky? Can he do that? Can he do it in normal conditions? Well, this is the closest we've gotten to documenting a falcon in, say, normal hunting conditions, not pacing a plane or something like that. What does he do in the real world? And so our maximum radar speed documented with wild bird hunting. Okay, when they reach 200 miles per hour, what they do is they are up in the sky and then they stoop. That means they're not flapping 200 miles per hour. They pull all their wings in and they just drop out of the sky, and their aerodynamic shape allows them to gather maximum force without any air resistance or very little air resistance. That's what they're doing. They're cutting through the sky. That's how they get to be as fast as that. So this guy took a radar gun, pointed it at wild birds hunting, and he clocked him at 114 miles per hour, which is a little short of 200 miles per hour in a hunting real world kind of scenario, not being thrown out of a plane or some other kind of strange, not usual circumstance. However, that was one guy with one radar gun, and he studied two birds. Okay. So the bottom line here is we have some very interesting anecdotes of individual birds doing things. We have a little bit of collection of numbers, some data, if you will, but you need to be truly data. You need to have studied multiple birds, okay, and gotten multiple readings if you're going to get a good idea of what birds are typically capable of, what their normal kinds of thing is. Okay, so anecdotes are not data. They can be informational. They can point you in a certain direction. They can get you started on a hypothesis. They can be useful in getting you some picture of the truth. But at the end of the day, you got to do some counting. You've got to do something that you can run some statistics on, that you can get some numbers on. Without those numbers, without getting some significance to your data, then you just have anecdotes. You have stories, you have information, but you don't have what we would consider proof of this. So that brings me to the last thing, which is just an editorial comment on this particular thing, is that why has no one done this experiment rigorously? Okay. And it's harder than you think. The reason nobody did it till 1999 was being able to point a radar gun at something. I mean, that was that's a relatively recent piece of technology. Okay. Or even accelerometers that you can put on a bird and measure what the results you get from that. That, the technology is just catching up to us. And but so far, last time I looked this over, when I get these presentations ready, I try to find this information, and I think I did a deep dive on this just earlier this year. I had not found anybody who published an actual set of data that was studying multiple birds in multiple situations to see how common this goes. So I would say, can peregrines falcon reach 200 miles per hour? That is true. Okay, we do have anecdotes to say that has happened and that it could happen. However, there's a point of skepticism in that I don't know if peregrine falcons do that routinely, or if it's only when they're being put in extraordinary circumstances. And I think that makes a difference, okay, about whether you can say how true that fact is. Is it something they do, or just something that we managed to get them to do by putting them in some weird position? Okay. No two snowflakes are alike. This is a very common thing that I think we've all grown up with. But then, I think about this and I think about, well, you look at your average snowstorm, there are a lot of snowflakes in a snowstorm. And think about all the snowstorms that happen in a winter, and all the snowstorms that have happened over the age of the Earth. Okay, through glaciers. I mean, there's a lot of snowflakes that have fallen. How likely is it that two of those snowflakes are identical? Well, when we say identical, we mean identical. Like all the molecules are in the same place in two different snowflakes. That's our standard, right? Because no two snowflakes are alike. The reality is there are thousands upon thousands of water molecules in a snowflake. Okay. And if you just shrink it down to like the minimum number to have like a lattice, okay, you still are going to need a lot. So the bottom line is there are so many water molecules and so many different ways that water molecules can be combined to form a snowflake that the odds of two snowflakes being identical are infinitesimally small. In fact, there are far more possible combinations of water molecules in a snowflake than there are atoms in the universe. That's how the numbers extrapolate. Okay. So the odds of two snowflakes, even given all of the countless numbers of snowflakes that have fallen throughout history, the odds of two of them being identical are infinitesimally small, but not zero. So there you go. Are no two snowflakes alike? There's nothing in the math that prohibits them from two snowflakes being alike, but the likelihood is so small that effectively, yes, you can have, there are no two snowflakes that could be alike because the odds of that happening are greater than all the possibilities of the universe for that. So there you go. So takeaway here is amazing facts can be true, but you don't know for sure unless you look. Okay, got to back that up. You can't just assume, oh, that sounds good to me, that no two snowflakes are alike. If you look at the real math, then you can back that up. The real math says, yeah, pretty good chance that they aren't two alike. Our last myth this evening is a bit of a tale of myths. What happens when you have a nature myth and you use it in a program because it's kind of a fun thing, even though it's not really 100% true, or share it with somebody, even though it's not 100% true. And that woolly woolly bears. So the idea is that, can woolly bear caterpillars predict the weather? And here's your handy chart for woolly bear weather prediction. Basically, the more black, the more harsh it's going to be. The more brown, the more mild. If the brown's on one end, it's going to be mild to begin and then harsher toward the end of winter. If the brown's on the other end, it's going to be harsh at the beginning and then wicked at the end, or something like that. Okay. All right. Well, how true could that be? Well, you may be skeptical already, and you should be. Here's Joe Boggs from the OSU Extension. He went out on one afternoon. He found himself 4 woolly caterpillars. And you can see that these 4 woolly bear caterpillars, predicted 4 different winters. Okay. So yeah, any woolly bear you pick up, they're unique. They're all going to have a little different combination of brown and black. And then the amount of brown and black can change depending on how many instars they've been through, how many times they've, change their exoskeleton and all that kind of stuff, and how long they've been growing. So the colors of the woolly bear really have there's no bearing. They're all random. Okay. The sizes are random. There's no way to do that. Well, but you hear it a lot. You still hear it a lot. And people often ask that. Okay. And I blame somebody for the fact that this little myth somehow sticks around and I still hear it. Okay. And I'm going to blame somebody for that. And I'm going to blame this gentleman right here. This is C. Howard Curran, curator of insects for the American Museum of Natural History from 1946 to 1960. Okay. And I have a picture of Life magazine up here for a reason. Now, this is Howard. He retired, so he looks like a happy guy there. He retired. He has since passed away. But back in that period of time, back in the between 1948 and 1956, while he was curator of insects, and he enjoyed engaging the public. He enjoyed teaching people about insects, and so what he did was he went out to the New York countryside where he had some property, and out there, just being a casual insect guy, he would collect woolly bears and he would see what they were predicting. And then he wrote a couple of tongue-in-cheek kind of articles for for magazines about this little quote study he was doing. It wasn't a real study. He was just having fun with it. And he said, "Oh, looky here. My woolly bears are predicting a harsh winter." And so in 1948, he did this. And guess what? There was a harsh winter. They had a big snowstorm that winter. Well, this just blew up his popularity. And it found its way in the Life magazine. And for the next several years, he did reports from the field to predict use the woolly bears to predict the upcoming winter and see how it went. From 1948 to 1956, they were lighthearted. They weren't meant to be something that was taken seriously. He was just having fun with it, but it created a little bit of a buzz, okay, about woolly bears. I'm not sure if everybody quite understood that he was not really being serious, okay? And it got picked up. It got picked up by popular media. In fact, and in the 60s, it got people so excited, they started doing woolly bear festivals. This seems to be an Ohio thing. But if you go out to Ohio, they have a woolly bear festival every fall. In fact, it looks like it might be coming up. This is the 2024 bulletin, but about this time of year, and they'll gather around and have fun with woolly bears and talk about watching the woolly bears and all that kind of stuff. Okay. So they're having fun with it, but it's kind of this weird thing where they're having fun with something, but the thing they're having fun with is not actually true. And so they were kind of perpetuating this idea. And I think that's how it gets stuck. And even today, you still hear this myth being said because it kind of got picked up and perpetuated by this guy having some fun with it. And it got in the papers and kind of blew up and became its own thing. And again, people are having fun with it, but technically, it's not true. It's a little dubious from a nature education standpoint. Okay, so there you go. There is the woolly bear one from 2024. I didn't find this year's. I was just grabbing a picture quick. I probably could find this year's. If you're really excited, you can go check it out. It does mean driving to Ohio. So the lesson here is that myths are powerful. You have to be careful out there. Okay, you could be having fun with something. You know, one of these things like a dad joke, where you tell something. You know, you tell your dad joke to your kids about. Well, watch out for the snakes might crawl into your sleeping bag tonight because you want to be clever, and then you end up with a child crying all night long because there's a snake crawling into his sleeping bag. So yeah, they're powerful. Got to be careful with them. Now, it's a serious business. We don't have any mislearning coming along. So let's review. Nature fact or myth? Raccoons wash their food? That is not true. Not observed in the wild. Wood frogs can survive freezing solid. That is true. A properly designed experiment did demonstrate it. Goldenrod aggravates allergies. That is false, but with an asterisk. If you stick your nose in the goldenrod, you might get a reaction. Okay. But it's not the one that's causing the allergy counts. It's ragweed, but related, but not the same. So give goldenrod a pass. Possums can hang by their tails. True, but only when young, only when they're small, and it's only a brief thing. They can't really like hang out that way for long. Possums can eat 5,500 ticks in a season. That's false. That's based on bad math, bad science setup, and it's not, ticks have not been found inside of possums. Plants breathe carbon dioxide. That is really false. They don't breathe carbon dioxide at all. They breathe oxygen like we do. They use the carbon dioxide for another purpose in photosynthesis. It is not the same. And so any carbon they bring in, they're going to exhale or decompose into at some point. So it does not, and it is not a breathing kind of use of carbon dioxide. Ben Franklin, the turkey, nope, he never did that. Okay, only tongue in cheek in an unpublished essay. Peregrine falcons, 200 miles per hour. That's true. They've been documented in a couple of situations with sensors to go that fast, but they haven't been documented. I put an asterisk next to this one because they have not been documented at that speed in the wild in a natural setting just yet. And I hope somebody will do that someday. No two snowflakes are alike. That for mathematically is as close to true as you could possibly get, even though technically you could have two. There's nothing stopping two being identical except the sheer unlikelihood of two matching up over time. And then woolly bears can forecast the weather. That is absolutely false. They cannot do that. We do have fun with it, but like a dad joke, you have to be careful a little bit with your fun that you don't create mislearning. All right, let's finish up with a baloney detection kit. Quick summary of how am I going to make sure that I know that this fact that I've learned, this amazing thing that I've learned, is it true? Okay. And this kind of applies to any part of life. Nature facts now could be facts in other parts of your life as well. Okay. The amazing fact. Beware the amazing fact. First of all, trust no one. All right. Just because you see it in an article or an expert says it, it doesn't necessarily mean that they have verified the information. They may be just relaying something that they heard or something they picked up without researching it. Okay. Or the researcher that was doing the research, you got to look at the study to see if it's done right. Okay. So look at it, see if it's true. Okay. The next rule is that absolutes are never absolute. When anybody gives you an idea that this thing happens all the time, or this thing never happens, or the animal always does this, or this is the most poisonous, whatever, those are usually a sign that there's an asterisk somewhere qualifying that idea. And the last one, probably the most important, is look for the literature. See if you can find some place where it's written down with some sort of study or reference attached to it. Okay. So something that's a scientific paper, that is better than anything else you can find written down. Okay. Even if it's something that's in a scientific publication, something that is data where they do numbers and statistics and analysis and multiple trials, and that is better than just a collection of stories that people are telling or observations people have made. It doesn't mean those anecdotes are useless. It just means they're not as valuable as actually going and counting the thing that you want to see and studying it in a formal way. And then the gold standard, if you find a nature fact, is can you find a paper that is researching your fact that you're checking out? Okay. And are they doing it properly? Okay. Oh yeah, it backs up your fact. Yay. Is the experiment properly designed? Does it have enough to do enough trials? Are they really testing the thing that you are looking at? Okay. And are the conclusions that they're drawing, are they backed up by the stuff that they are collecting, the information, the data that they are collecting? Now we can also do the same thing with the preschooler inquiry model. You know, a preschooler inquires. How a preschooler verifies fact. He simply asks the question, why? And then he asks again, why? Okay. And then why? So, why is the sky blue? Well, because of nitrogen. What? because of the chemicals in there in the air. Why are those chemicals in the air? Well, because they've been there since the starting of the planet. Why? How did they get there? Okay, well, they got there from space. How did they get there? Why are they there? Why were they in space? Well, they were created by stars. All right, so I'm going cosmological with it, but you get the idea. Okay, it's like peeling back an onion. All right, so you find this fact. Well, where'd this author get this fact? And where did the fact come from? And what was the paper? Is there a paper that supports this fact? And does this paper is this paper a study, or just a collection of a collection of anecdotes? And is it properly done? Okay. The person saying this, are they somebody who is truly a scientist, or are they just somebody who likes to pick up a blog, somebody publishing a blog and just saying whatever cool stuff they've learned? Okay. So always